Hello and welcome to my lab video, which is for lab 2, which observes the motion of a falling object. The goals of this experiment are to observe motion of an object dropped from rest and moving slowly, indicating that it's affected by forces other than the force of gravity. And then based off of this, to construct two computational models based off of Newton's second law, one including gravity alone and then one including both gravity and drag. And then the main result of this experiment was that an object affected by air resistance will fall at a slower rate in comparison to an object in free fall. The fundamental equation that was used in this experiment was the momentum principle, or Newton's second law, which says that the net force on an object is equal to the change in momentum with respect to time on the object. So you can see the derivation of that equation as well as the units that are used in this experiment. And then this equation allows us to predict motion on an object based off of initial and current conditions, which helps in the formation of both computational models. The system in the surrounding was the paper, and the surroundings were the air, the door, the ground, anything that wasn't the paper. So the initial conditions and general process of the experiment was that a piece of paper was selected and altered so as to cause a straight trajectory downwards. Its mass and dimensions were recorded as well. The paper was held at rest and the recording started, and then the paper was dropped and its trajectory was recorded as it descended. The video was analyzed in Tracker, and then the experimental and computational models were formed based off of the data points from the Tracker video. So 3 models were created in this experiment. An experimental model that was created based off of the video, and then a first computational model that was constructed with glow strip that demonstrated an object in free fall only affected by the force of gravity. And then the second computational model demonstrated the motion of an object that was affected by both the force of gravity as well as the drag force opposing that motion. So the Tracker model or experimental model follows the video that was taken for the experiment, and then once the data points were plotted against each other on Excel, you can see how position and time do not vary directly with each other, indicating a non-constant velocity. The first computational model follows the motion of an object that is only affected by the force of gravity. Similar to the Tracker model, you can see the object follow a similar trajectory in that it demonstrates a non-constant velocity, and the curving in the graph would indicate that the object is moving with constant acceleration, which is known from the gravity force. And then you can also see the code right there, which is also linked in the description. The second computational model introduces the drag force into the equation and attempts to recreate the data extracted from the Tracker video as accurately as possible. The equation used for the drag force was that the force is equal to the drag constant multiplied by the velocity of the ball. And so you can see, similar to the Tracker video, the object ends at the same spot and follows a similar trajectory. And then a comparison of all of the models, the drag and Tracker trend lines both start and end at the same point and all follow similar pathing. And some differences, the first computational model with just gravity observes a quicker rate of change between position and time, which indicates that the paper would fall faster with no drag force. And then there's some slight deviation in the Tracker line in comparison to the glow script equation for drag, which leads us into our error analysis. First off, some random error. In the video, the paper fluttered slightly on its trajectory downward, even though you guys haven't seen the video. Take my word for it. This would affect the placement of the points to track the motion, which would give an explanation to the slight deviations on the graph towards the end. In addition, there could be human error in the placement of the mass points, and then it's possible that the point was not placed in the exact center of the paper, which would then affect the placement of data points on a graph. In terms of systematic error, the deviation in the free fall trajectory and the trajectory with drag, as discussed on the last slide, drag force directly opposes downward gravity force, and thus the object would fall at a slower rate in comparison to motion with no opposing force. So what does it mean? So terminal velocity describes the point during free fall where drag and gravity force balance each other out, causing the net force on the object to be 0. So graphically, displacement in time would eventually vary directly, leading to like a straight line in a constant slope, which would then confirm constant velocity and zero acceleration, or no net force. The models with drag confirm this, as they both start off with a non-direct constant proportionality and slowly begin to demonstrate that direct variation towards the end as the trial continues. And then since the time was so low, the terminal velocity was not reached, but if the object were maybe dropped from a higher point, perhaps this terminal velocity would be reached. And then if the object were to be thrown downward, the force of the throw would continue to affect the object's motion, which would lead to the terminal velocity taking an even longer time to be realized, as the drag force would have to balance out not only the force of gravity, but the downward throwing force as well.